Hi, everybody. This is Mario Levesque from Mario Explore. Today, our guest on our podcast is Dave Mansel Thomas, an eminent geologist that I work with and that I know for quite a while. And I think he can enlighten us and make us discover exactly where oil and gas come from. Uh, and that's going to be a great show. Dave, how you doing today?
Oh, I'm very well, thanks, Mario. Thank you for your invite.
Thank you for being here. Dave, can you tell us a little bit about your background, where you come from, and what brought you to geology?
Yes, of course. Well, I was born in West Wales, which is a country to the west of England, and its main economy when I was growing up was a mixture of coal mining and agriculture. But as time goes on, the only industry left there now really is agriculture. In my youth, my passion was to join the Royal Air Force. And indeed, I got a flying scholarship from them. So my career really was in aviation. Unfortunately, by the time I was 18, my eyesight went, and that career path really was not for me. So I decided to do geology, and I graduated from London University with a joint degree in geology and in chemistry. My first job, just after that, was in. It took me a few months to get a job. It took nearly 2 months. Was in the Republic of Indonesia, where I was a well site geologist in the jungles of Sumatra and Kalimantan. In the North Sea, I learned the importance of economics in the commerciality of offshore gas fields when in 1975 we found a real giant gas condensate field, but was not exploited for a number of years due to cheap gas from the southern North Sea, the cost of building a condensate pipeline, and really it was the mixture of capital expenditure versus reward. In North Africa, I was with Occidental Petroleum and worked on some of the major oil fields in Libya. And I was offered a job as chief geologist with the international subsidiary of Kuwait Petroleum Corporation, and we had interest in 12 countries from Italy through Africa to Indonesia again. Uh, I was a consultant for a number of years, consulting for oil companies and also for institutions and even certain West African countries. I was founder of a small oil company, and we were on the London Stock Exchange. And we, after a few years, we sold out to a major oil company. I joined Utica Resources in 2018, as I was then, as I still am, excited, enthusiastic by the natural gas potential of the St. Lawrence lowlands. That is why I'm here.
Dave, thank you for this extensive resume, and thank you for being here with us. Dave, with the audience, I'd like them to understand how oil and gas is created, and I've got a set of questions to ask you that I think may enlighten the people on how it's done. First, what is the geological process that contribute to the formation of an oil basin?
Well, first of all, Mario, if I could just say to you, what is geology based on? And it's based on the concept of uniformitarianism. It's a fundamental tenet in geology that suggests that present day geological processes can be used to understand the Earth's geological history. First spoken of over 200 years ago by a geologist named James Hutton. It has been the guiding principle, really, in geology, contribute to our understanding of the Earth's processes, history, and evolution over time. For example, sand on the seashore, limestone corals in the warm seas of the Bahamas, or say in the Great Barrier Reef of Australia, mud, silt, and rivers and seas, round pebbles in rivers, coastal erosion, icebergs, Arctic and Antarctic cold. The Earth has seen it all before. What we see today is what happened in the past. So from that, I can go and answer your question, or a series of your questions, I assume. Uh, we'll start off with what you just said, is what geological processes contributed to the formation of an oil basin. An oil basin is a sedimentary basin which consists of layer upon layer of sedimentary rock and of different characteristics, which has the capacity to generate and hold oil and gas.
Okay, does it have to be in the water, or it could be? Does erosion do that also?
From erosion, we get the sediments. Everything is eroded. Mountains are eroded until there's nothing much left. The Appalachians, for example, were as high as the Rockies at one time, but they're very, very old, and they've just been eroded. Now, to erode a mountain, it has to go somewhere. The erosional product has to go somewhere, and it goes into a sedimentary basin.
Okay, so it goes down to the creek and the river, and
It goes down. It's carried by the rivers, which is a fluvial process, or it can just go straight into the sea.
okay,
Like you have
directly.
cliffs that are eroded, so it's carried out into the sea, and then it's carried then by currents, and it builds up a sedimentary layer. And over time, then it's layer upon layer. I mean, you must have seen, Mario, on the seashore, where you look at a rock, a sedimentary rock, and you see layers in it. The
Right.
reason you have layers is because it's a different process that laid each one down. It could be a fine-grained sandstone, or it could be pebbles. What it means is you have different geological processes.
Actually, where I come from, there's a place called Miguasha, and we used to go there. And it's a place where you find fossil, and it's those kind of rock that they're all layered like that. And this is exactly what you're describing right now.
Yes. And you see, to come to what I'm sure you're interested in, what role does sedimentary rock has in the creation of a basin? Well, um, we have in sedimentary rocks, we have uh, um, three factors really that generate and hold oil and gas. First, we need a source rock to for this oil and gas. Source rocks are rocks um, that contain sufficient organic matter to create hydrocarbons, then subject to heat, temperature, and time over time uh, to produce hydrocarbons. Source rocks are usually shales or limestones.
Okay,
Uh,
so those sedimentary rock hold the like the plant and all of that
yes,
has been carried with it, and this is where it's born. So this is what we call the source rock.
that's right. And then, of course, if you have the source rock, what you then need is the reservoir rock, which are rocks that have the ability to store fluids inside their pore space, so that the fluids, whether it'll be water, oil, or gas, can accumulate. In petroleum geology, one of the elements of a petroleum system is that it can accumulate hydrocarbons. So we've talked about reservoir, and we've talked about the source rock, and the third is the trap to actually hold the hydrocarbons in place. And it's an impermeable rock. It stops the oil and the gas from going up to surface, and
Could it be
that is how it's accumulated.
could it be different kind of rock, or
It could it,
formation?
it could be it could be a shale rock. It's usually a shale rock, which could also be a source rock, but not necessarily.
Okay.
It doesn't
That
have to be a source rock. It
that
could be
that's quite
barren. It could
complex.
be nothing in it, no organic material in it. But it's a good trap. I tell you, an excellent one is usually anhydrites or evaporites or salt, for example.
Okay.
That is very impermeable, and some of the major oil and gas accumulations of the Middle East, Saudi Arabia and Kuwait, have 1,000 feet or 5 to 1,000 feet of salt as the cap rock that
Wow,
it can't escape.
that's good. Uh, do you see a difference? And what you described there, it's how it's formatted, the formation and all of that. But how physically do you find that? How do you know where it is?
Well, that's a very good question. If I can take you back through history, in the old days, people found oil where there was oil seeping from the ground. Um, in the US, in the United States, for example, I'm sure you have met him. He's a bit too old for you now, Mr. Drake, who found oil in Pennsylvania, but he found that around an oil seep. So in the early days, at the turn of the century, last century, they drilled or they looked for oil where there was oil escaping onto the surface. For example, and one of the biggest discoveries was at Spindletop in 1901, and again there was oil coming out of the ground, or at least seeping out of the ground there. And when you stood on the surface, you could see a slight undulation because there was salt in the subsurface pushing up. The salt then formed a trap, and the oil then, which was or the source rock, which was below the reservoir, just migrated into it.
Wow, and I remember that I read that Spindletop produced 100,000 barrel a day at the beginning.
Yes, yeah. Well, it was mad. You had these wooden derricks just about everywhere, and there was so much oil produced that it in fact the market collapsed. And this is when the Texas Railroad Commission came in to try and bring some order to the market.
That's interesting that you bring that because this is one of podcasts that we should do. All those body of regulation who was born, but a lot of people don't know that the Railroad Commission was overseeing the oil and gas in Texas, and
Yes, that's right. That was back in those days,
that's really interesting.
a long time
So
ago.
so at the beginning they were finding that like that, but now that the easiest oil seep and they're all pretty much been discovered, I guess. How do we do it now?
Well, again, after drilling around the oil seeps, which is where oil was found in the Middle East and in Iran, for example, and also Azerbaijan, um, you had gas seeps there, and of course the gas seeps in Azerbaijan became a religion. In essence, this is where Zoroastrianism originated from, the worship of fire. But as you said, as the years and the decades went on, where do you find the oil if it's not that obvious? So we then turn to the use of seismic, and the seismic technique is bouncing sound waves off the subsurface. You set off an energy source. It could be dynamite or sound of some sort or another, and it goes down through the earth and it bounces back depending on the density of the rock, of the type of rock.
Yeah,
And we can then work out the architecture of the subsurface. So we're looking then for a three-dimensional trap. And then, of course, what about that's, yeah, fine for the trap, but what about the source and the reservoir? Well, this is where, in the old days, again, the field geologists came in with a geological hammer and went out looking for samples, analyzing the samples, and doing it that way.
breaking rocks all over. Uh,
Breaking the rocks, looking at the source rock, looking at the content, for example, of the source rock, and then looking for reservoir rock. And if these three can come together, or even if just one can come together, you will find somebody prepared to take the risk, take the monetary risk of drilling a well in the hope of
to
finding something.
to go and see what's going on. So one of the important part is to know where it was 400 million year ago, all those basin were, and that helped with the discovery. The job of a geologist is a lot like an archaeologist also to
Yeah.
to understand how it was millions of years ago.
No, absolutely right. For example, I think you've said it quite well. For example, if I was an archaeologist on a dig and I found a bowl, I would say, "Look, this is a bowl. We use bowl today. We drink from a bowl, or we eat soup from a bowl."
Yeah,
And it's the same with geology. I come back to uniformitarianism. What we see today, the sand on the seashore, for example, rivers, this this has been going on in throughout Earth's history, and we can go back to nearly 4 billion years.
that's interesting. And talk, talk to me a little bit about the tectonic and how it influence and how you guys deal with that in the oil and gas sector.
Well, in it really is a very, very interesting and fascinating subject. That is plate tectonics. It was in the year 1596, Mario, that a Flemish cartographer, Abraham uh, Ortelius, noted that the coastlines of Africa and South America appeared to fit together, and he put this down to earthquake or earthquakes plural and floods.
Yeah,
And yet that's what he thought. That's 400-500 years ago, and yet the theory of plate tectonics is really a young science. It wasn't until the 1920s that a German meteorologist, climatologist, put together his theory of plate tectonics, and he called it continental drift, where continents move apart and continents come together and push into each other.
that's interesting. And this is where the Pangea and the other supercontinent come from. The split and going back and forward like that. Dave, let's talk about the tectonic and how it influence the discovery and because I think it's important that for people to understand the Earth movement and how it's done and where first of all where it come from and to appreciate the work that you're doing.
Yes, of course. Well, tectonic plates are large slabs of rock that divide the Earth's crust and move constantly, reshaping the Earth's landscape. The system of ideas behind plate tectonics theory suggests the Earth's outer shell, it's called the lithosphere, is divided into several plates. Just think of it all as being cracked. And they glide over the Earth's rocky inner layer above a soft core, which is probably molten, which also gives, incidentally, our magnetic field. Most geological activity comes from the interplay between these plates where they meet or divide. The movements of the plate creates three types of tectonic boundaries. You have convergent, where the plates move into one another. Then you have divergent, where they move apart. And we talked earlier about Africa and South America.
Yeah,
And the third one is a transverse or the transform, where they just slide up against each other. Think of the San Andreas fault system, for example.
yeah,
And of course, um, when these things happen, also you can imagine that sedimentary basins are formed, because when you push something against something else, if you do it with a piece of paper, you can see the paper starting to undulate. Well, this undulation will give you a sedimentary basin.
in Inglewood in California, in Los Angeles.
Yeah, or the San Joaquin Basin, for example,
Okay,
is another good example. Um, I mean, sedimentary basins are regions of the Earth's crust that are dominated by subsidence. They 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 go down, and the subsidence provides depot centers then for the sediments. The more sediment you pile on, a lot of basins will just continue to just deepen.
okay,
And some of these basins can be up to 10 kilometers thick.
wow.
And that gives a really excellent chance. And remember of geological time, and that gives a real excellent time frame for us to have our reservoir, our source rock, and our trap mechanism in place.
If we compare that, Dave, to what's going on with the St. Lawrence River and the Gulf of St. Lawrence, that means it could possibly be a good reservoir in a few million years from now.
Yes, indeed, absolutely right. If you think of the amount of sediment that comes down the St. Lawrence. But years ago, I was in the Congo. I was in Brazzaville, and I was having a drink, looking out over the River Congo, and the sun was going down. It was quite a magical moment. I could see in the over also in the west were the lights of Kinshasa, and I what was coming down. The River Congo was so wide; it must be about 4 or 5 miles wide at that point. Was a whole tree. The tree trunk was the diameter of this tree was huge, and the whole thing was just going down the river out to sea, out into the Atlantic Ocean. And I could say to you that within probably 4 or 5 million years, that tree will be gas.
So we understand now that uh, to create oil and gas, you need those sedimentary basin. You need to carry also organic matter.
You need to carry organic matter, and the sedimentary basin is filled up slowly, but it gets filled up over geological time with more sediment, which makes the source rock interval that we were talking about, it's it's now under extreme pressure because of what's on top of it. So as you go deep, as you know, into the earth, it gets hotter because we've got a molten iron nickel core. So as we go down, it's known as geothermal gradient. As we go deeper into underground, um, it gets warmer, doesn't it? So if you've got pressure of the sediment on top of your source rock interval, and you've got temperature, and you've got time, this then converts the organic matter into hydrocarbons, whether it'll be oil and gas. Now, some plants will become gas, others will become oil. And in time, the oil will also break down into gas because oil, as you know, Mario, is a long chain polymer, a carbon and hydrogen, and it'll break down under
Yeah.
temperature, extreme temperature, to give you methane, and a carbon residue is what's left.
Methane, like you said, it's the last form of hydrocarbon before it become either hydrogen or carbon. Because we know with old basin, and we have that in Quebec here in around Sherbrooke. It's too old, and we said overcooked, and basically what's left in the ground,
Yes.
it's only carbon. Okay, Dave. Now I'd like us to talk about the Utica Shale, which is something that you know and you understand. And that first of all, how do you characterize it? How do you characterize the Utica Shale without going into any specific, but any not being technical?
Well, the first thing I have to say about the Utica Shale is how extensive it is. It is in Ohio, it is in Kentucky, it is in Virginia, it's in New York State, it's in Pennsylvania, and it's in the lowlands of Quebec. And in all these places, it is a gas producing reservoir. In fact, the only place where it hasn't been produced commercially to the advantage of its citizens is Quebec.
Yeah.
And the beauty of the Utica Shale is as follows. I talked earlier about source, reservoir, and trap. Well, for the oil or for the gas to go from the source rock to the reservoir, it needs a migration pathway. It needs to be able to migrate there. It needs to be able to travel into the reservoir. And once you start considering that, there's a lot of risk involved. And it's a probability argument of whether is it probable or possible that the source rock can go into the reservoir. Is it possible or probable also if the reservoir is sealed by an excellent cap rock or an impermeable layer above the reservoir? These are things that have to be thought about. And in exploration, what we do is we look at the probability. What's the probability of finding a source rock? What's the probability of finding a reservoir? What's the probability of migration? What's the probability of the timing of all these things that will give you a successful accumulation of oil or of gas? The beauty of Utica Shale is, and in the lowlands, in the St. Lawrence lowlands, is forget all of that. What we've got is, and what we do know, is that the Utica Shale is a world class source rock. The beauty of the Utica Shale is that it is its own reservoir as well as being the source rock. We don't have to think about, include migration, possibility and probability of migration. Does the oil or the gas need to migrate anywhere to go into a reservoir? And is the reservoir of sufficient volume, or the pore space of sufficient volume that it can hold commercial quantities of oil or gas? Is there a cap rock there that will hold it all together? We don't need any of that. In the Utica Shale, it's all there. The Utica Shale is a world-class oil and gas resource, proven, and also the fractures in it make it an excellent reservoir.
So what you're describing, it's when we know where the Utica Shale is through seismic, through all different observation that we made, it become almost an industrial development. The risk of finding something is not there because we know that the rock itself is the reservoir, and with hydraulic fracturation that we can go and recuperate this gas. Is there any specific geological indicator or marker that geologists use to identify potential oil formation? And because, like the Utica, how it's been discovered, what were they looking for back then?
Well, if you look at the wells, the exploration wells that were drilled in the St. Lawrence lowlands going back to the 50s, they were just looking for hydrocarbons. And what they found was a rock which certainly has oil in it and gas in it. One of the problems back in those days was the techniques, was the drilling techniques and the production techniques to get it out. What has developed over the last 3 decades really is fracking and horizontal drilling.
This is what made the difference right now. And like you
That's
said,
been
because
made a big difference in the states. The Barnett Shale, for example, and all these other organic rich shale units that has oil, condensate, and gas in them.
yeah, I read somewhere that the principal cause of the decline of coal in United States, it's exactly what you described: hydraulic fracturation and directional drilling, which led to having really cheap natural gas and in surplus. So it's been really,
Yes.
really help. If you love the environment, you should love those techniques.
No, I think you're absolutely right.
Yeah. Dave, on maybe not the last word, but on on a technical level and on the evaluation level, we talk about a world class discovery here. And do you have any idea or knowledge of how, if we develop it, what extent it could be to maybe
Well,
comparison with other basin or size wise or
oh, size-wise, well, we calculated just on Utica Resources lands or permits, we looked at 18 trillion cubic feet of gas, which is an awful lot of gas.
that's a lot.
Um,
It's about 80 year of what we use in Quebec.
yeah. So it's a shame. It really is a shame that the government is not prepared to use its own natural resource.
That's right. And but look, we're gonna keep pushing, and we're gonna keep informing people, and people like you. I think it's important that what you're doing today for people to understand what's oil and gas and where it come from, and how we can develop that. And this is the goal of our podcast that we're gonna do on a regular basis: bring information to the people, bring credible information to the people, which is really important. Dave, thank you very much for your time today. It's well
It's been a
appreciated,
pleasure.
and hopefully we'll be able to develop it.
Yes, I hope so too. Thank you, Mario.
Thank you, my friend.
Okay, thank you.
Thank you very much, everybody, to have been with us today on our podcast. Thank you for following us, and please do like us on our different social media that help us to reach people. If there's any question, please feel free to contact us. We're there to educate and discuss with people and bring the right information at the right place. Thank you again, and follow marioexplore.ca.